in this video we are going to discuss the design of relay ladder logic using Huffman method. So you might have heard about Huffman method. It is usually used for designing asynchronous sequential systems. Mostly in these are mostly used in digital electronics. So we are using Huffman's method to design relay ladder logics. So the methodology that we are going to discuss was first introduced by Pesson in a journal called Using Programmable Controllers for Sequential Systems with Random Inputs. Uh, so we will be discussing the method introduced in that paper. So first of all, what is the need? What is the advantage of this method? Is there any benefit or not? Yeah, the main objective is to minimize the number of relays used in the relay ladder logic. So we might think, why should we bother about reducing relays in a ladder diagram? Because we are not actually using any kind of relays nowadays. We are just entering those into a PLC, which is fairly powerful. But why are we using that? The motivation behind the design was so by reducing the number of relays, the length of the program that is to be entered into memory could be reduced. So the motivation was to avoid longer programs. Then the second motivation was a longer program is difficult to understand. So to avoid that, a longer program is difficult to understand. And another motivation was the it will take a larger program will take a larger memory, so larger memory will be taken, and since the program takes a larger memory, it takes more time to scan all the memory addresses. So this so in to reduce all these things, a method was suggested by Pesson called Huffman method, and we will discuss that method with the help of an example. So consider an alarm system, which is, so let this be an alarm system, and alarm system. So there are two inputs. Assume that there are two inputs. I will change the color of the pen to indicate inputs. So both of these are the inputs. Let's name them x1 and x2. And let me take a different pen. This will be the output, z1 and z2. So there are two inputs and two outputs. So x1 represents the danger signal. So this is an alarm system, so some kind of danger must occur for it to activate. So x1 is the danger signal. A sensor senses some danger and sends a signal, and that signal is x1. That signal acts as the input to this alarm system. And this is a push button, and Z1 is a siren. So when there is a danger or when there is an emergency, a siren must go on. So that's the output of alarm system. And Z2 is the warning light. Z2 is warning light. So it works like this. Say if there is a danger or there is some emergencies occurring in some part of the factory or somewhere, a danger signal will be activated. So let me take another color to indicate all those. Uh, okay. When when there is a danger signal, then immediately the siren will start making a lot of sounds, and then somebody will come, somebody will recognize this danger or this emergency, and the as a part of acknowledgement from that operator, there is a push button which he must push as an acknowledgement that he has seen that danger signal. So this is a push button. That operator will push the push button. So when this push button is activated, the siren will go down, means it will stop making noise, and a warning light will be activated. So light will remain active as long as the danger signal is removed. So when the means after pushing the push button, the operator must go to the problematic areas and remove the danger. And after the danger is gone, the danger signal will this signal will go off, and then the warning light will go off. This is the operation of alarm system, and we wish to implement this alarm system using a relay ladder logic. But we could simply draw, by using intuition, we could simply design a relay ladder logic, but we will use Huffman's method in this example. So first we will draw a flow diagram containing different states. Means each states means for example, at our initial stage, the x1 was, there was a danger signal, the x1 was activated, and at that time z1 got activated. That is a particular state, and we will draw the state flow diagram. Let me scroll down. Yes, now we will indicate different states inside a circle. The state will look like this. The input will be, states will be written in this fashion: x1 x2 slash z1 z2, and we will use 1 and 0 to indicate whether which signal is activated and which signal is not activated. So if x1 is 1, it means that there is a danger signal. If x1 is, there is a danger signal, and if z1 is 1, then it means that the siren is currently making sound, the siren is activated. If it is if z1 is 0, then it means that the z1 is not activated, it is low. And if x1 goes low, it means that the danger is over and there is no danger signal. And similarly for push button and warning light, if you push the push button, then it will be indicated by 1, and if you remove if the push button is removed, then it will be indicated by a 0. Similarly for warning light, when warning light glows, the Z2 will be 1, and when warning light goes low, it will be 0. So using this, we will represent different states of the system. Means the different state which the system can be at. So the first state will be, let me make it smaller so that you can see everything both in the same screen. Yes, first we will, the first state is that nothing happens, no danger, there is no danger signal, push button is not activated, therefore there is no siren and no warning light is glowing. So yeah, that states will look like this, means everything will be zero. A danger signal will be inactive. uh, x1 x1 is the first one, so danger signal will be inactive. Then x2 will also be inactive, 0 0. And then we will have a slash, and after that we will indicate z1 and z2. So siren will be off in this case, so siren will be off, and warning light will be also off. And we will, this is the first state, and we will encircle this. So this indicates the first state, and we will name it as 1. Now the next state is, second state is, if what happens if a danger signal is present. So when a danger signal is present, x1 will become 1, and x2 will be 0 because no push button has been not activated, so it will be 0. And when x1 becomes 1, z1 siren will go high, so z1 will be 1, and the warning light will not be activated because warning light will be activated only when push button is activated. So warning light will not be activated, and this is the second state. So operator, uh, the danger signal happened, and now the siren is making all kind of sounds. This is the state 2. Then the third state is something where the operator arrives at the scene and uh, push the push button, and so the push button is also activated. So x1 will become, x1 is still 1 because the danger still persists, and since the push button is activated, x2 is also 1, and we will have a slash. Then z1 and z2, when the push button is activated, so this is kind of an acknowledgement, so siren goes, siren siren becomes inactive, so it will become 0, and warning light will be high. So as long as the danger is not averted, warning will still remain high. So this is the third state, and the final, and then there is one more state, state 4. So what is the state? That it the state is when dangers in this state, the push button is removed and the warning light still persists. This is the next state, 0 1. So fourth state means that the after the operator push the push button, he leaves the scene to rectify the danger, and that state is called that state is the fourth state. Now after, so the we can now draw the flow diagram. So from first state, uh, when a danger signal arrives, the system goes to the second state. Then when the operator arrives and push the push button, the system goes to third state. And when the operator leaves to rectify the danger somewhere else, the system will go to fourth state. And after the problem is rectified, the system will return to the original state, which is state 1. Let me redraw it. It will go like this, So the system will return to state 1. Now, these are the 4 basic states, but there are some other states also will which the system will have, which the system will experience and or encounter. So we will see those states also. So what happens? Let me scroll down. Okay. Now, what happens if uh, assume that there is no danger signal or there is nothing wrong about the system and there's no danger signal is activated, but accidentally an operator or somebody else has pushed the push button. So that state can also occur. So if that state occurs, the warning light should not glow. So that state is indicated by this. This is some kind of an accidental case where somebody just pushes the push button accidentally, and if the warning light glows, no, if Z2 will become 1, it will be a problem because it will give a false alarm to everybody else. So if that scenario occurs, no Z2, that means warning light should not glow. So that will be an additional state which we will name as 5. So this happens from state 1. So when everything is all right, and there is no problem, somebody accidentally pushed the push button, and so from 1 to 5 it goes to from 1 to 5, and suddenly it realizes that since there is no danger signal involved, it suddenly goes back to the original state. And there is one more state, when when the danger signal occurs and the system moves to state 2. So x1 is 1 here, the danger signal is high, and the operator has not yet pushed the push button. The push button is not yet activated in this case. So before the operator comes to the alarm system, before that itself, if the system if the danger signal is removed automatically, uh, something happened and danger scenario is removed, then uh, the system will go to another state. Means after the second step itself, the system has gone to a better, danger signal is removed, so it will go to 1 will become 0. So since the danger is not there, 0 0, and but the siren will still be there because in this state. And after reaching this state, so if this state is reached, then the system should automatically go to the state 1. So since everything is rectified, so system should go back to state 1. So it will go through this path. Means somebody comes and acknowledges the push button should be pushed, and somebody comes and it is pushed now like this. So the operator pushes the push button, but there is no danger signals involved here, and it will return to the initial state. So we will name the state as 6. Now there is one more scenario in which so what happens if somebody accidentally pushes the push button without any danger, but after reaching this state a danger signal occurs, and where should it go from here? So it can go from here to, so suddenly the danger signal means this 0 will become 1 and a new state is formed. So what will happen? So we can design it such that it goes from 5 to this state. because since the push button is already pushed, we can skip the step of the siren being activated and all. So since the operator will be there near to the alarm system, so we can avoid that scenario, or we can design it such that from this it goes to a, a state where the alarm, we can define a new state in that case, but we can avoid the number of states now, total number of states, so this will be okay. And if the danger signal is removed from after reaching the state 3, if the danger signal is removed again, then it can return back to this state. So danger signal is removed and it goes from here, and then after reaching 5, then it will return to the first state, and everything will be normal. Now, so there is some extra additional cases which is actually the probability of it happening is impossible, but we will still draw those cases. What happens when both signals, and that is x1 and x2, changes simultaneously? So the happening of that scenario is very less, but we will have to consider everything, so we will just consider it. So from 0 0 initial state, x1 and x2 is 0, both 0. What happens is when both suddenly becomes 1, means danger signal is also there and push button is also there, both arrived simultaneously, but that does not occur in real life. There will be some kind of delay, so there is no, but still we will consider it. So we will indicate it with dashed lines. So x1 and x2 both changes to 1 and 1, from 0 to 1. So we will indicate it as dashed line. So this scenario may occur since there is a danger signal, and since the if both changes, we will want the system to move from state 1 to state 3. If both input x1 and x2 changes to 1 simultaneously, we want to move the system. We want the system to move from state 1 to state 3. So this is like this, and if again from state 3, if both signals is gone, if both danger signal and push button is removed simultaneously, if that happens, we will then there is no problem. We can skip the step 4 and we will go back to the initial state. That is also, since again why this is an impossible scenario, because there will these are practical systems. There will always be a delay between each operation. The probability of both occurring, means the arrival of the danger signal and the pushing of a push button happening simultaneously is very low. So but still we need to consider everything. Now there is one more case. Okay, not one more, there are two or three cases more. So consider state 2. If we look at state 2, here also both signal can change simultaneously. That is, x1 can become 0 and x2 can become 1 simultaneously. Here also the possibility is less, but still we will consider it. So what happens if these both signals changes simultaneously? Means this becomes 0 1. If this becomes 0 1, we will look. So we have already a state 5 which has the input 0 and 1. So we will want to move we will want the system to move from this state to state 3 immediately. In that case, if both becomes 0 and 1, x1 becomes 0 and x2 become 1, we will want the system output to be 0 0. So the corresponding state is this 5. So we want the system to move from state 2 to state 5. And similarly, if the system is currently is in state 5, and if both the input signal changes simultaneously, that is x1 becomes 1 and x2 becomes 0. We don't want a system like this, means 1 0 0 0. We don't want a system like this. So I will write it once more. If we don't want a system like 1 0 0 0, so we want to avoid the number of states, and also this is kind of dangerous actually. There is x1 is 1 and there is a danger, and no response from the output. This is kind of dangerous, so we want to avoid this scenario. So to avoid this scenario, we will want the, if x1 become 1 and 1 and x2 becomes 0, we want the system to move from here to here. So, and so there is one more case in state 4 also. If we look at state 4, we have already discussed state 3. If 1 and 1 becomes 0 0, then it should move to state 1 immediately. And similarly in state 4, if it becomes 0 and 1, if state 4 input becomes 0 1, we don't want this is kind of state. This is an additional state. We don't want that. We have already 5 states. We don't want to increase the number of states the system to be in. So we will force the system to move to state this state. So this is the complete state diagram, and we have drawn all the state diagram. This may seem a bit difficult, but actually it's all right. Once you have some experience, it will be all right. And now we will move to drawing a flow table. After that we will reduce that table, and after that we will derive an expression, and after that we will design the relay ladder logic. Now let's move to the flow table. So this is what we have drawn currently is called flow diagram. Now we will draw flow state. Here also I will make this a little bit smaller. Try to scroll it down. Yes, okay. Now we will draw a table which will I will draw the table in right side. I will use a different and okay. So the table will have a row and a column. The columns indicates the inputs x1 and x2. We will write it down. So x1 x2 can take 4 combinations, right? 0, there is 4 combinations: 0 0 1 0 1 1 1 0 and okay, there is a 0 0 0 0 1 1 0 1 1. Okay, there are 4 states. We will write it down. We will write it down in this order. Okay, observe this order: 0 0. After that we will write 1 0, and after that means each subsequent if you write subsequently for each one you have to change only one digit. So 0 0 1 0. After that we can't write. We will change in this order: 0 0 1 0 1 1. Okay, 0 turns to 1, and finally we will write 0 1. We will write in this order, and these are x1 x2. x1, x1, x2. Now in the rows we will write different output combinations. So there are 0 0 1 0 0 1 0 1. We will write the outputs corresponding to all the states. Okay, we will just write it down. We will write 0 0, then the next is state 2 is 1 0, then there is a 0 1, then state 4 is also 0 1, state 5 is 0 0, and state 6 is 1 0. We will write it like this. And so this is the method suggested by Huffman, so we just follow it for now. And we'll draw a column. Yes. We'll just draw a row and columns for this could be confusing if you write without columns and rows, if you don't draw all this, so it's better to draw it now. Yes, everything's over. Now we will use we'll use black. We have not used black pen till now, so we'll just use it. So we will start writing the different state number, that is it could be 1 2 3 or 4 3 4 or 5 or 6 whatever. So we will just write it down one by one. So let's start from the first top left row, top left cell. So 0 0 0 0, this is the state 1. Then next is uh, 0 next is 1 0 0 0. So 1 0 0 0, what is that state? Just look at this table. The when 1 0 means the danger signal has arrived and the output is still 0 0. So this means this is an intermediate state, means this if there is a delay, so there is always a delay for the siren to be activated. So there will be a delay for the siren to be activated. So there will be an intermediate state where let me draw it once more. So this is the 0 0 0 0 state 1. From while going from state 1 to state 2, 1 0 1 0. So there will be a state when the system has detected an input danger signal. A danger signal is inputted into the alarm system, but due to some delay, the siren has not yet activated. So this is an intermediate state between 1 and 2. So we will simply write it as 2. This 2 is an intermediate state. It is an intermediate state moving to 2. So we will write 2 here. And now next is 0 0 1 1. 0 0 1 1. Let's look at this 0 0 1 1. Where is it? Oh, no, I'm sorry. This 1 1 0 0 means x1 x2 is the we should, it is written like it is x1 x2 z1 z2. It's like written like this. So 1 1 0 0. Okay, 1 1 0 0. Where is that state? Yes, it is. It is starting from state 3 to state Yes, yes. This is also an intermediate state. Uh, Starting from here, mm, in an improbable state, we have told you that there is an improbable state 1, 2, 3. So this is an intermediate state. That is both input is activated, that 1, 1, and but the output is yet to respond. So this is the intermediate state. So this is an intermediate state going to 3. So we will write it like 3. And also now next is 0, 1, 0, 0, 0, 1, 0, 0. Let's look at where is the input. 0, 1. Yes, this is the 0, 1, 0, 0. This is state 5 simply. Now now let's write the next row. 0, 0, 1, 0. Where is 0, 0, 1, 0? This state 6, 0, 0, 1, 0. Now let's write 0, 1, 0, 1, 0. State 2, then 1, 1, 1, 0, 1, 1, 1, 0. Where is it? So if you don't see the state here, you must look for intermediate state. Okay, 1, 1, 1, 0. Yes, 2 to 3. 2 to 3 is the 1, 1, 1 intermediate state. Means the push button is pushed and it is activated, so it will become 1, 1, and the output, there's a delay, so output remains 1, 0. So there is an intermediate 1, 1, 1, 0 here, 1, 1, 1, 0 intermediate here. So that is the, so since this is going to 3, the system is going to state 3, we will write it as we will fill that column as 3. Now there is 0, 1, 1, 0. 0, 1, 1, 0 means, where is 0, 1, 1, 0? No, there is no state here. The stable state is not here, so we must look for intermediate states. 0, 1, 1, 0. Let's look at one more time. Yes, yes. This is the 0, 0, 1, 0. Means this dotted line, dashed line is when both inputs change simultaneously. So when the system is in state 2 and both inputs change simultaneously, that is x1 becomes 0 and x2 becomes 1. So this 0, 1, the output still remains 0. Output still remains 1, 0. So the intermediate state is 0, 0, 1, 0, and since this is going to from 2 to 5, we will write it as 5. Now we will start filling the next column. In the next column, if you understood from till this part, you can just fast forward here. I will just enter everything, every column from now on. Now zeros in for 0, 0, 1, 0, 1. We will look whether there is a intermediate state or not. 0, 0, 0. Yes, 4 to 1. The system moves from 4 to 1. Scroll a little bit. Yes. When the danger signal is, look at for state 4, when the danger is removed, the input becomes 0, 0. So from 0, 0 to the output, if there is a delay, so then this is input intermediate state where 4 to 1, from 4 to 1. So we will write it as 1. and now 1001. 1001 is a where is answer for straightforward. It is straightforward. There's no doubt for that. Now stage 3. No, 1101. 1101 is stage 3. And then 01 0 0101. Is there a stable state here? Yes, 4 to 5. This is an intermediate state from 4 to 5. 0 C1 0 1. Intermediate state from 4 to 5. The similar logic that I explained before. Now next row. This is similar. This will be a similar row because same output, same z1 z2 is there, so it will be similar. We can simply write it down, and this row will repeat the first row 1 2 3 5, then 1 0. This will repeat the second column 6 2 3. Now we have completed the flow table. This is the flow. This is called flow table. Flow table. We have completed the flow table. Now we will reduce this table. We will merge this table, and we will call it the merged flow table. So how to reduce the table? So before that, we will look for stable state. Uh, so now that we have drawn the flow table, we will encircle some numbers indicating the stable states. So we will look at each rows. So each rows represent each states. We have written the output like this, right? 0 0 0 1 0 0 1 1 0 1 0 0 1 0, in according to this numbering state numbers. So in row 1, the stable state is 0 0 0 0, which is this. Another thing. Okay, this is the stable state here. There are in row 2, the stable state is 1 0 1 0 1 0 1 0 is this, and here this is the stable state, and row 4, this is the stable state. Now here this will be the stable state. Here this is the stable state. So the encircled states are the stable states, so the rest are intermediate states. And we will, based on some rule, we will shorten the flow table, which we will call as merged table. And let me make it smaller. Okay. And this is the flow table. We will the the merging of table rows. We will merge some of these rows and we will make this table a bit smaller, but this will be done according to the following rules. So rule number one, if you have that PDF with you, you can refer that PDF also. Rule number one, if a given column, I will write it down, if a given column has both an unstable and a stable state, the merged row gets the stable state. Second rule, if a given column has both a number and a dash. So the dash indicates that there will be some, for examples, where we will not have anything to fill. So there will be no states or intermediate states. Means this combination there is not possible. That kind of some examples will be there. So in that case, the merged row gets the number with or without if it is an encircled number, it will get the encircled number. That's all. Or without the circle. Now the third rule, if a given column has only dashes, the merged row gets a dash. So using these laws, these rules, we will start building a smaller table. So I will explain these rules by doing the example. That will be better, I think. Yes. Okay. Now, so if a given, we will look at the column. If a given column has both stable and unstable states, we will merge so there is one more thing, we can't merge any column, so the numbers must be same. means the column must contain the same numbers. For example, we can merge this row and this row, but we can't merge the first row and second row because all the numbers are here. Here the state is 1 and here the state is 6, so we can't merge it. Similarly, we can also merge this row and the last row, similarly like that. So apart from this, we have to follow these rules also. After that we can merge. So we will just number the rows for convenience. 1 2 3 4 5 6. Okay, we will first merge row 1 and row 5. Yes, row 1 and row 5, and we will write it down. Okay, here we will 1 comma 5. We will just write the numbers 1 2 3 5. We will write the inputs also. Here it was 0 0 1 0 1 1 0 1. So the row 1, the first row and fifth row was merged. So there is one more thing, the numbers should be same. So there should be no contradictory numbers for the same input output combination. So here the input output combination is 0 0 0 0. So there should be no contradictory numbers. So we will just merge the number that are similar numbers. So row 1 and 5 are merged, and now by you, if you look at the first rule, so if a given column has both an unstable and stable state, the merged row gets the stable state. So if you look at row 1 and 5, this both contains 1, and the final row will get the we will not use this intermediary state 1. We will simply use the circled state. Similarly, there is one more circled state here, 5. So here there will be 5. Now we will merge rows 2 and 6. Yes. 2 6 will be merged, and 2 and 6. So the states will be 6 2 3 5. Yes. 2 3 5. So 6 would be circled, 2 would be circled based on these laws. Just read it. And the third merging will be 3 and 4. 3 and 4 will be merged, and the numbers will be 1 4 3 5. 1 4 3 5. So the circled state will be here, 4 4 and 3. So these are the reduced state diagram. We will copy it. Control C. We will take a new page and paste. Okay, this is the new merged table. Merged flow table. Now we will, so each row denotes some output, so we will assign a state. So from this we will develop some equation, and based on this, that we will we will draw the ladder diagram. So each row signifies a flip-flop, a state of a flip-flop. Each row signifies a state of a flip-flop, and so here there will be 3 flip-flops, and the states of the flip-flop are as shown. So these are the state assignments. So we will be row 1 and 5, y1, y2 and y3. So we can see that the output corresponding to these are from the previous table. We can just see that 1 and 5 contains the output z1 z2 as 0 0, 2 and 6 contains 1 0, and 3 and 4 contains 0 1. So it is, we will just write in bracket 0 0, it is 1 0, 0 0, yes, and we can, so the y1, y2 and y3 will represent the outputs of that flip-flop. I told you that each row can be each output can be represented by a flip-flop, and each, so the outputs of each row will be y1, y2 and y3, and y1 will represent, just if we look at this, we have z1 and z2. So if the output of the flip-flop of this row is 1, then it will represent, it will tell you that z2 is 1, no, z1 is 1, this is in the order z1 z2. So z1 is equal to 1, and if the flip-flop corresponding to this third row becomes 1, it will represent z2 is equal to 1. So z, we can simply assign the states of, assign the outputs of this flip-flop as our output, so our system output, that is z1 is equal to y2 and z2 is equal to y1. So we can get this output, and so those outputs of those flip-flop will give you then the outputs z1 and z2, and after designing all these things we will see that the system will work as we designed. We will see that. So there is 3 flip-flops. So what kind of flip-flops are we using here? We are using RS flip-flop, set reset flip-flop. So this is S and this is R input. So if you, there is 2 inputs here. If you give 1 here, there is 2 output also, Q bar. So if you give a high to 1 to S, so applied people and digital computer science people can understand this, but it might be a bit difficult for students to understand these flip-flops. So this is an example of RS flip-flop. So this output works like this. If you give a 1 at the S input, this means this is set. S means set, and R means reset, simply speaking. So if you give a 1 here, the output Q will be 1, Q will become 1, and Q complement, this is the Q complement is the complement of Q, so this will become 0. And if you give a 0 here, then the output will become 0 and Q bar will become 1. Similarly, in the reset terminal, if you give 1 here, the output will be 0 and 1. If you give 0 here, this will be 1 and 0. So flip-flop works like this, and for each rows we will have assign a flip-flop like this. So this will be R, sorry, This will be S R Q. So this will be Y1. Similarly, there will be one more flip flop S R. This will be Y2, and there will be one more S R. Okay, this will be Y3. So from looking at Y2, from looking at this, we can tell that if Y2 becomes 1, this will indicate the output Z1, and if Y3 becomes 1, it will indicate the output Z2, because if Y2 becomes 1, so here Z1 is only become 1, so we can assume that we can represent Z1 by Y2. Okay. Similarly, we can here only Z2 is 1, so when Y3 becomes 1, we can represent this Y3 using we represent this Z2 using Y3, just like that. And so how does this work? The this is totally incomplete right now. So how will this give Y1 Y, how will give this give us the proper output? How will there be any state? How will this work actually? So this will work like this. Means uh, we will find the inputs to be given to these flip-flops, means S and R, both these flip-flops input will be designed such that based on this floor table, we will design it such that it is a function of x1 and x2. Okay. S R, both there are three flip-flops. We will name it S1 R1, S2 R2, and S3 R3. S1, S2, S3, and R1, R2, R3 will be designed such using the input X1 and X2. That is the danger signal and the push button, or some combination of these X1 and X2. We will design S1, S2, and S3, and we will design it such that it follows the state flow diagram. It exactly follows the state flow diagram. We will design the entire system based on this. So why are we using flip-flops here? So we are simply using some of the techniques used in sequential circuits, and we are applying it in ladder diagram. That's all. So the Huffman's method was basically used to design sequential circuits. So, but we are simply using it for ladder diagram. That's all. Now we will start designing the values of. Here also there are some laws how to design this. I will copy paste this once again. This table is very important, so I will copy paste this. As Control C, and here Control V. So this is the state assignment. So now we will start writing the equation for S1, S2, S3 in terms of X1, X2, and sometimes Y1, Y2, Y3 also. We will use everything we can to get our desired system. So if you want to go to state 2, how will you go to state 2? Before going to state 2, there will be an intermediate state 2 here. So you must go from I will draw yes. from state 2 to the unstable state. This uncircled 2 is an intermediate unstable state. It must go, if the system is in this state, it must go to state 2 immediately. So if you want to reach state 2, the only way to reach the second row is from state 2. So the output of the second row is y2. So now we will start with designing the input S2 corresponding to the flip-flop, which corresponds to the second output, second row. So if you want to reach the second row, there is no other intermediate state. So there are only two stable states in the second row, 6 and 2. You can only reach there from, you can reach from either actually you can't reach from anywhere. Well, there is only one option for you to reach the stable state, the second row. It is by from first row. That is, you have to reach from first row, that is this unstable state 2 to stable state 2. So effectively the only way to reach the row 2 is from row 1. So the state corresponding to that, we will mark that state and we will find the address of that state. So what is the address of the state? What does you mean by address of the state? The address of the state is the combination of this input, the product of input and output written in terms of x1 and x2. So 1 0, this will indicate x1 x2 complement, x1 x2 dash, and the output is y2. So the address of that unstable state is x1 x2 into x1 into x2 dash into y1. This is the this address. So if it reaches, if the system is in this state, if or in this row, it will automatically go to second row based on that thing. We will, so the input to the second flip-flop will be designed as like this. So S2 is equal to the address of this row will be taken. I will remove the circle because it will create confusion. So S2 is equal to this one. X1 means 1 corresponding to x1. If it is 0, x2 complement. So here similarly here it is x1 complement x2, x1 into x2. Here x1 complement x2. It is written like this. We will use the product of this and this, y1 into this, y1 into x1 into x2 complement. So the input of the second flip-flop is the input of the second flip-flop is this, y1 into x1 into x2 complement. Yes. Similarly, we will write the, so how will now for getting S3, we will look how can we get to the third row, how can we get to the third row from, is there any way we can see that? Now if you look at here, the only way to reach the third row is through this way, from 3 to from the intermediate state 3 to the stable state 3. So this will be the address here. But you can see that there is one more way. There is here also there is a 3. From here also we can directly go to row 3. So there are two ways. If there are two ways, we can write it like this. So there we can the address, so it will be the addition of address of both these three. So y2 into, here first we will take this y2 into x1 into x2 plus y1 into x1 into x2. So we can write it like this: y2 plus y1 into x1 x2. So there is one more rule regarding this, that is, if a row contains only one number, that is, here in this row there is only 3, there are 3 threes, one is circled. Similarly in this column there are 3 fives and one is circled. If a condition like this happens, we can we will just take the column address only. We will just take the column address only. So S3 will become x1 into x2. We will only take this. We will not take the product of output. So we will just take this. Now we will design S. So now we have seen S1, S2, and S3. So how will you get to S1? From where will you get to S1? The answer is from row 3. From row 3 you can get to S1. But this is not the only way. We can also reach to S1 from this way also, 5 also. There are two ways to reach that. So this is also intermediate state. So we, in this case also, we will just add this thing. We will write here s1 is equal to the address of 1. Here we will use this. I will remove the circlement. It will cause confusion. So s1 is equal to x1 dash into x2, x1 complement into x2, x1 complement into x2. Complement means if x1 is equal to 1, x1 complement is equal to 0. So if you have confusion like this, this is the idea. If x1 is 1, x1 dash is 0. That's all. So s1 is equal to x1 dash into x2 into here there are no repeated numbers since the year 6, so we will have to take this unique address, so we will multiply it by y3 also. Plus there is one more way to go to row 1. How? From this column 3. But here there are 3 inputs. There are 3 numbers, just like previous case. So we can write y2 plus y3 into x1. We will write this way. x1 dash x2, but we can rewrite it like this: y3 plus x1 complement x2. So we have found out the equations for s1, s2, and s3, but also we need to find the equation for r1, r2, r3 also, because we want the system to reset automatically after everything works. So we will give proper reset signals also. So there is one more condition: if one of the flip-flop is active, the other two must be inactive. Other two will be 0. there is no there is no state which contains the output 1 1. Okay, z1 and z2 is there is no case in which both are simultaneously 1. So if one of the flip flop is uh, set, then other must be reset. Now there is one more thing. So we will start with this one. So when the system moves from y1 to y2, that is, when the system moves from this state to this state, the previous state must be reset, right? So what will you do? The we will the means this we will assign now we will apply reset. We will look at the design for reset signals. So if you look at this, the from the unstable state 2 in row 1, it will go move to the stable state 2 in row 2. And so the when it reaches the stable state 2, the first flip flop which corresponds to the first row must be reset. So the reset signal R1 will be the address of the stable state 2, that is y2 into this one, y2 into y2 into x1 into x2 complement, y2 into x1 x2 complement. But there, if you look at here, there is also one more transition can occur here. From row 1 there is one unstable state 3, so a transition can occur from row 3 to row 1 to row 3, that is stable in unstable state 3 to a stable state 3. Such transition can also occur, so we must consider that possibility also. So in if one either of the two cases happen, the reset signal must be the first flip flop must be reset. So we will add that condition also, that is we will add the address for this row also, that is x1 into x2 into y3. So we will add that y3 into x1 x2. Now for R2, from R2 there are two possibilities. Either it can go from this unstable state 3 to uh, stable state 3, or it can go from this unstable state 5 to stable state 5. So if either of those occurs, uh, reset signal must be applied to uh, second flip flop. So we will combine the addresses of this stable state 3 and stable state 5. So the addresses of stable state 3 is y3 into x1 into x2, y3 x1 x2 plus stable address of stable state 5 is y1 into x1 complement, y1 into x1 complement or x1 dash to x2. So we have got the equation for R2 also. Now we will consider R3. Yes, 3. So from third row there are two. Here also there are two possibilities of transition from unstable state 1 to stable state 1, and from unstable state 5 to stable state 5. Here we will write R1 as the combination of addresses of one stable state 1 and stable state 5, that is y1 y1 into x1 complement x2. I will write it once more. I will remove from here. I will write it here. yr3 is equal to y1 into x1 complement x2 plus y1 into there is a complement here and complement x2. So these are the two states. So these are all the combinations, and this equation can be simplified also, or the equation for R3 can be simplified further, and we will get an equation like this. Let's write it y1. This y1 and x1 complement we will take it outside into x2 complement from plus x2. So x2 complement plus x2 is 1 in Boolean algebra. So we will get y1 into x1 complement. So we have got three equations for r1, r2, r3, and we will implement this. That's all, and thus we will finish this thing. So before that, how are you going to represent a flip-flop in ladder diagram? We will see that. So a flip-flop can be represented like this in ladder diagram. So generally, these are the two rails. We will connect a push switch here, and this will be the set input, and we will connect a normally closed push switch also here. This is normally open, and this one is normally closed, and this will be our reset button. We will connect an output coil, and we will also connect a normally open relay in parallel with the push set, because this is the push switch. Once we push the switch and remove our hand, it will go to its normal state, but we want this output to be one continuously, so we will add a parallel path also. So once we push the switch set, once this is one, when set is activated, the output coil gets activated, and once reset is activated, means from normally closed position to normally from open position, if it goes like that, the circuit is broken and coil will get deactivated. So this is a representation of set RS flip-flop. Here what we are doing is, instead of this push button, we are changing it from this to these equations. So if this is R3, we will change this push button from this to this. Similarly for set also. That's what we are going to do now. So I will simply draw everything now. Once more thing, we saw that since we are using here normally closed switch, we must do some kind of modification here also. So instead of this R2 means, if R2 is 1, only the reset button is. So if the idea is that if this R3 is activated, or this contact must be open. And so that's the logic we will use relays to realize that logic. We will try to do that. So just for example, we will use R1 just for S1 and R1. We will see whether we can implement that or not. So the S1 S2 is a bit simpler, so we will first start with S2. That's better because it's simpler. So S2 is equal to first equation. S2 was y1 into x1 into x2 complement. Now where is R2? R2 is y3 x1 x2. It's we simplified it, right? So R2 is R2 we did not simplify, so y3 x1 x2 plus y1 x1 complement x2. So we will use this is R3 S2. First we will use this part. So we will realize S2 like this. We will draw a normally open relay for y1. This is y1. This we are ANDing all this. If you have seen the video for the basic ladder diagram, so you can see that for getting AND operation you have to connect it in series. So we will connect all these three. There are three inputs, so there are three components here, so we will have three relays in parallel. For this part we are actually deriving this part. Okay, so this will be y1, this will be x1, and this is x2 complement. So either we can write here x2 complement, or we can use normally closed switch and write it x2. Okay, so this part is realized. Here we will use this will be written like this. So this is y2. This is the output coil itself, the representation of output coil. So once this is active, from this path the current will start to move. And now the reset part. So how will you implement the reset part? Let's see how can we do that. Actually when this becomes one, the here the contact must be broken. Okay, so how can we achieve that? To achieve that we must take the inverse, we must take the complement of R2. So let's try to take complement of R2. That is when actually R2 is equal to 1 in flip-flop, but in our arrangement R2 this must become 0. When R2 is equal to 1, this this thing must become 0. So we will find R2 complement. So when R2 is 0 1, then R2 complement will be 0. So we will find that. I mean we will implement that. Oh, let's see how can we find it. So this is actually big. So y3 x1 x2 complement into y1 x1 complement x2. The De Morgan's law, we will apply the De Morgan's law, and we can split this thing. This is right. To I have changed the symbol, right? Means if you I will skip all this step. I will simply write the end result. You can do it yourself using the Morgan's law. This will take a lot of time. So I will skip all those things because I have changed symbol in between. That's why. So you will get R2 complement something like this. R2 complement is equal to x2. You can verify. I am just copying it from the textbook itself. So you can verify it by yourself later. Now we will, corresponding to R2 complement, we will write, we will connect this x2 and we will connect it in series with this. This will be our output y2. So thus we have successfully implemented one of the flip-flops. So we will have to find everything. I have copied the final ladder logic from the PDF here. So this will be the final ladder logic. So let's verify everything. So let's just verify one more. Let's see. S2 is equal to y1 x1. We have already seen that. S3 is equal to x1 into x2. So both relays are connected parallel. And has been S1 has been a little bit modified here. Y3 into x1 complement into x2 complement plus x1 complement into x2. So everything is correct. You have to find R1 complement, R2 complement, R3 complement also, and then you will get these values also. These are R1. This is R1 complement, R2 complement, and R3 complement. You have to find that and verify that whether these are true or not. Okay. And y2, as mentioned here, y2 and y3 represent z1 and z2. So after implementing this system, you can see that it will follow our desired state flow. It will perform according to what we have designed. Okay. I hope you got an idea of what Huffman's method is. So I hope this is enough. So you have to go through that paper also. You have to read it very carefully and you have to work it out. I have skipped some of the calculations R1, R2, and R1 complement, R2 complement, etc. So you have to work it out yourself. So bye.